Welcome everyone to Étale cohomology on November 12th, 2020. So today is exciting. It's hopefully it's the last day of foundational material. And so hopefully at the end of the day today, we're going to start proving the Weil conjectures. So in particular, we almost have enough to do the rationality and functional equation, and then we'll start talking about the Riemann hypothesis. Okay, so let me remind you where we were. So last time we finished sketching Verdier duality, although very sketchily, and we started the Lefschetz fixed point formula, at least some special case of it. And I'll discuss slightly fancier versions later on, but let me just remind you what the setting was. So we had a smooth and projective variety, and one can drop both of these words if one is a little bit more sophisticated, over a separably closed field. And we had a morphism phi from x to x. And what we did is we tried to understand the fixed point set. So the way we wrote that is we took the intersection of the graph of phi with the diagonal. So this is an intersection of cycles in x cross x. It's an intersection of cycles of complementary dimensions. So this intersection is a zero cycle, and when I write the dot, I just mean the degree of that zero cycle. So for example, if phi has a finite fixed point set, then this is just the number of points in that set counted with multiplicity. So if you'd like, the finite set is that intersection of the graph of phi and the diagonal is a finite scheme, and you can take the length of that scheme as a case scheme. And we wrote that as the following sum. So it was the sum from I equals 0 to twice the dimension of x of -1 to the I trace of phi, and I think this should actually be I plus 1, sorry about that, the trace of phi on hi of x with QL coefficients. Okay, yeah, and it should definitely be I plus 1, because if I, sorry, it should be I, sorry about that. Yeah, it should definitely be I. Yeah, so maybe it's worth noting, so what's the, so let me actually give you an example of this, which we can prove with no effort at all. So if x is just a disjoint union of copies of spec k, then what is this saying? So we have phi from x to x, and this is saying that the number of fixed points of phi is the trace of phi on, well, h0 of our finite set, which is just QL to the x. So functions on x with values in QL. Okay, and this is almost trivial. This matrix phi acting on this finite set is just a permutation matrix. So the fixed points correspond exactly to where there are ones on the diagonal, and so that's the proof. Are there any questions about this kind of example? It's a little silly maybe, but I do genuinely think of the Lefschetz fixed point formula as like a generalization of this example. And it's actually a fun exercise. So if you take like a graph or even like a nice simplicial set and a simplicial morphism, you can really, well, like a finite simplicial set or finite simplicial morphism, you can really make this into a proof of the Lefschetz fixed point formula, although it's not totally trivial. So I recommend you give that a shot. Like, it's really fun. It's not trivial, but it's fun. All right, and last time we also did the example of curves, or of sorry, P1 with the map like z goes to z to the n, and that I hope you found fun too. Maybe one more fun example, which I'll leave as an exercise. So suppose you have any map f from P1 to P1. Well, how many? So let's say it has degree d. So how many fixed points does a degree d map from P1 to P1 have with multiplicity?
b plus 1.
Yeah, it has d plus 1, right? Because a polynomial has d roots and then infinity, for example. That's an example situation. Yeah, and so then you should try to prove. So we did this in the case x goes to x to the n, but it works in general for degree n polynomials, and you should try to prove that the Lefschetz fixed point formula is true in this case. All right. Cool. So last time we began the preparations for the proof. So the preparations were the following two lemmas. Let me just state them. So lemma 1 was a sort of reinterpretation of pullback through phi. So it was given a morphism phi x to y, where here x and y are both smooth and proper. Although you can rephrase this in terms of compactly supported cohomology, and then it will be true in more generality than that. And given y in the cohomology of y, then we could write the pullback of y through phi as sort of cupping with a cycle class. So what it was is if we write the projections x times y, here we have the projection to x we called p, and the projection to y we called q, then we can write this phi star y as p lower star of the cycle class of the graph of phi, cupped with q upper star of y. Okay, and I left this as an exercise. It's almost tautological, so it follows from like the definition of the push forward and the projection formula, which we also talked about last time. It's worth doing if you haven't done it yet. There's a few things to pay attention to, which I just want to briefly remark on. So first of all, this cycle class here is not in, it's not, at least canonically, in the cohomology of x cross y with coefficients in QL. It lives in the cohomology of x cross y with coefficients in a twist of QL, namely you twist by a power of the cyclotomic character corresponding to the relative dimension of phi here. And that goes away because this p star also has the opposite twist. Okay, so that's one thing to pay attention to if you want to do this carefully. The other thing I wanted to mention is like, okay, like I drew a picture of this last time. So what you're doing is, let me try to draw the same picture again. So here's the graph of phi. Here's some cycle class y. And what you do is you take the preimage of the cycle class. Sorry, this is a picture. When I say cycle class, I just mean cohomology class. Sorry about that. So you take the preimage of this cohomology class, which you can think of maybe as being a geometric object if you are topologically inclined. You take the intersections with this graph, and then you push forward. So you look at the image down here. So that's morally the meaning of this proposition. It says that pullback, so if you're like taking preimages, is the same as intersecting with the graph and then kind of pushing forward. So here this green thing is q star, is phi star of y. So I want to just mention, I mean, there's an object in functional analysis, which is called a kernel function. So if you have a map between two kind of function spaces, one can often write it as integration against a kernel. Are you all familiar with this? Or does anyone want to? Yeah, great. Yeah, so here that's morally what's happening here. So if you imagine in de Rham cohomology, this is literally the case. So if y is a class in de Rham cohomology, so a differential form on y, so we pull it back to the product, so that gives you a function on some kind of product function, an element of some kind of product function space. Then cupping with the cycle class of this, well, this is also going to be represented by a differential form. So it's just wedging the differential forms together, and then this p lower star is integrating along fibers. So in de Rham cohomology, this is literally like integrating against a kernel. And so sometimes people call this like the kernel formalism, even in algebraic geometry. Like there's you can think of this as representing this pullback as kind of integrating against a kernel. And I think that's a useful thing to keep in mind, since later on we'll actually do things like maybe we'll replace y here with a sheaf, and this will be some kind of sheaf on the product. And so that's sort of a sheaf theoretic analog of integrating against a kernel. Cool. So here the proof I left as an exercise, and you should do it. All right, and then lemma 2, I just got to the statement at the end of last time. And what was that statement? It was, so here we wrote pullback along phi as integrating along the cut product with the cycle class, if you'd like. That's at least the sort of intuitive description of that lemma I've been trying to give. So now I wanted to describe how to understand the cycle class of the graph of phi. So we need to write that down more explicitly. And so what was the lemma? So we let EIR be a basis of HIXQL, and F2 dimension of X, FI 2 dim X minus R be the dual basis of H2 dim X minus R XQL. So then the claim was that the cycle class, so the cycle class of the graph of phi was just the sum of phi star EI tensored with FI. So I'm going to suppress the superscripts if that's all right. All right. So for example, and yeah. So what does this actually mean? So this means, so here where we view EI tensor FJ as a basis for the cohomology of X cross X with QL coefficients via Kunith. So this cohomology ring of X cross X is just the tensor product of this with itself, so or this with this, and so this, given a basis of each side, we get a basis of the tensor product, and so we're writing things in that basis. So in particular, phi star of EI is a linear combination of EIs, and oh yeah, sorry. So this should be an R here. So thank you for correcting me, Jose. All right. Are there any questions about the statement? So just as an example, maybe before the proof. So if phi is the identity map, then we're saying that the graph of phi, which is just the cycle class of the graph of phi, well, that has another name. What's another name for the graph of the identity map?
The diagonal?
Yeah, it's just the diagonal. That's exactly right. So the class of the diagonal. Sorry, let me write it this way. So that says that this is the sum of EI tensor. Let me actually use the superscripts here. FI, so this is 2 dim X minus R. Okay. So why is that? Well, it's because the identity, pulling back EI through the identity is just EI, because the identity acts via the identity map on cohomology, just like it does on any functor, on the output of any functor. All right, so let me sketch the proof of this. Well, are there any other questions before I sketch the proof? All right. So first of all, we can just immediately write the class of gamma phi as the sum of some AI tensor Fi for unique AI in the cohomology of XQL. Can anyone tell me why this is? So this is just by Kunitz. So this is because the cohomology of X cross X is free as a H star XQL module, as a right H star XQL module. Right, and what did we do? Well, this cohomology of X cross X is like the tensor product of this with itself. So that's just like if you pick a basis of H star XQL, let's say the basis EI, that means that it's a direct sum of copies of this, one for each basis element, right? And so that tells you that it's a free module. So in particular, these Fi are a basis of H star X cross X as an H star XQL module, right? Are there any questions about this? So the question is just like, what are the AIs here? So now let's compute the AIs. So the goal is to show that AI is phi upper star of EI. So let's compute the right-hand side. So phi upper star of EI. Well, by our previous lemma, we can write that as cupping with the cycle class of the diagonal. So that's P lower star of the cycle class of the diagonal cupped with Q upper star of EJ. Sorry, of EI. Sorry, of EI. Right. I mean, this is just our previous lemma, our kind of kernel formalism. So we can rewrite. I mean, let's rewrite what we're trying to prove. So this is said the cycle class of this graph was just the sum of AJ tensor FJ, and now we're cupping that with the pullback of EI. Okay, but now EI and FJ were dual bases, right? So let's write this again. So this is P lower star of the sum of AI tensor FJ. Here, this is AJ tensor FJ. This is sum over J, cupped with Q upper star of EI. Okay, now there's something to unwind, which is you have to remember what the cup product, how the cup product was actually defined. So the cup product was defined by a cup product on the product and then pulling back along the diagonal. So once you unwind that, sorry. So let me rewrite this. So what we can do is we can just write this Q star of EI as one tensor EI. That's maybe an easier way to say this. Say what I was trying to say in words. Okay, and now what do? We just cup formally. So we cup, the cup product is it respects the tensor. So we get that this is the sum over J of AJ tensored with FJ cupped with EI. Okay, so here's a question for you. What is FJ cupped with EI? So my hint is to remember that EI and FJ were, yeah, so Jose says it's the Kronecker delta function. That's right. So the point is that FJ and EI were by definition dual bases, right? So I mean, we just chose FJ to be the dual basis of EI. So that means that everything disappears except for the term where I equals J. So we get P star of AI tensor EI. to AI tensor, sorry. So what is it? What is, when you cup these things together, so what you really get is it's not quite the Kronecker delta. It's like the Kronecker delta times the generator of the top cohomology, right? So like, what is the pairing here? It's like we cup into top cohomology and take the trace. So what we really get is E of the sort of the basis element in degree 2 dim x. So this is what we really get. Cool. So now we're done. So why are we done? So this thing is, how should I say this? This thing is just P upper star of what's the right way to say this? Sorry, yeah. The right way to say this is that this is just AI. So why is that? So like, how did we define P lower star? So we defined P lower star via Poincare duality. So what that means is it's precisely the thing, so that P lower star of AI tensored with this equals AI. So here you have to think a little bit about what Poincare duality tells you. It tells you that you're using the fact that the trace of this is 1. Okay, so the bottom line is that we're done. I mean, what did we want to show? So we wanted to understand how to write the class of this graph as we wanted to show it was phi star EI tensor Fi. Well, we wrote it as AI tensor Fi, and then we computed that the AI are the phi star of EI. So that completes the proof. Okay, and then the thing you should check is that this push forward of AI, push forward of something tensor E1 of 2 dim x is actually that something. Yeah, and yeah. Yeah, cool. All right, so now let's prove the Lefschetz fixed point formula. So this is going to be a sketchy proof. So proof sketch of Lefschetz. So what I'm going to assume, as usual, so I'm going to assume that that the cycle class map sends the intersection product to the cut product. All right. So what do we know? So we know that the class of the graph of phi, we just proved it's the sum of phi star EI tensor Fi, and applying this to the identity as in our example from before, we get that the class of the diagonal is EI tensor Fi. So if you believe this fact that the cycle class map sends the intersection product to the cup product, then we get that the class of the intersection product is the cup product of these classes. So it's the class of it's the class of gamma phi cupped with the class of the diagonal, which we can write as follows. It's phi star EI tensor Fi cupped with the sum of EI tensor Fi. All right, and now let's see. So how do we do that? So we might as well actually. So maybe I'm going to switch these, which is harmless. So why is that harmless? It's because the class of the diagonal is the class of the diagonal. It doesn't matter whether you put the FIs on the left or the right. Right? It's literally the same sum. like you could have chosen Fi to be your original EIs, and then the EIs would be the dual bases. All right, so let's rewrite this. So what do we get when we write this? So let's see. So on the right-hand side, except sorry, yeah. So when you do this, well, okay, we'll see what happens in a sec. So you get a sum of phi star EI Fi tensored. Sorry, let me put parentheses here. Tensored with, well, what do you get when you cup Fi with EI? So what do you get when you cup Fi with EI? So we already discussed this last time.
Should you get 1, but also should these indices be the same, or maybe one should be J's and not I's?
Oh yeah, so what we're going to do is distribute the sum. So we'll see things disappear. So you don't quite get 1. You get the top cohomology, the generator of the top cohomology. So you get 1 when you apply the trace, right? So the pairing is trace of cup, not just cup. Yeah. So let's actually do let's do a sum over I and j and see what happens. I j. So we'll get the sum of phi star EI times Fj tensored with Fi Ej. Let me write it this way. So this Fi Ej, so this is E2 dim x, if you'd like, for I equals j and 0 otherwise. So we lose all the terms where I doesn't equal j, and then we get the sum over I of phi star EI Fi tensored this E2 dim x. Okay, so now what we want to show is the ultimate claim is that the sum over phi star EI Fi is the, so this is a number, if you'd like. So the trace of this. So the trace of this we want to equal to the trace of phi. And then there's up to a sign issue. So there's -1 to the i's, which is something I'm going to drop in this sketch. So the sign issue here comes from, there's some graded commutativity in the cup product, which when I switch these things, you get a so when I switch the EIs and FIs here, you get a sign, which I omitted because I don't want to keep track of it. So that's where the sign comes from. So let's ignore that. Okay, so can anyone tell me, why is this the trace of phi acting on H star? Anyone? So this is just a linear algebra fact. So if you have, so my claim is that if EI is so the claim, which if you haven't seen this before, you should check. The claim is that if EI is a basis of a vector space V, and EI dual is the dual basis, then the trace of A is the sum over I of EI dual evaluated on A of EI. Okay, and why is that? Like, these are literally the diagonal entries of the matrix EI, of the matrix A, right? Okay, so this is the proof. Okay, so what you should take away from this is that it's almost formal, actually. So it's sort of formal from this fact that the cycle class map sends intersection products to cup products, and from the computation of what these cycle classes are. So the Lefschetz fixed point formula is like, the deep part of it is this parenthetical. It's not the formula itself. Okay. Are there any questions about that? Okay, so there's a missing kind of bit that I want to talk about a little bit. So here's a question for you. So here rigorously, I guess we've defined. So like, what is this number gamma phi dotted with the diagonal? So right now the only rigorous definition we have is you look at the cycle classes and you take the cut product and it's some number. Okay, and a more computable version of that is like, if you believe this claim that the cycle class map sends intersection products to cut products, is you can take the intersection product of the two and then take the degree. But that's like at least not so obviously a computable thing. So for example, if these things, if their intersection contains a positive dimensional component, so for example, if phi is the identity and then you're taking the intersection product of delta with itself, that's not like a finite set. And in general, like gamma, like phi might have fixed points with multiplicity. So you have to know how to count them. So the claim, and this is a claim in just Chow theory. So the claim is that gamma phi dot diagonal equals the number of fixed points of phi counted without multiplicity. So in other words, the multiplicity of each fixed point is 1 if the following three things are true. So if x is smooth, if the tangent space, well, let me rewrite it in a slightly better way. So if the multiplicity, let me just write it this way. If the multiplicity of each fixed point is 1, okay, and there's a soft way to check this. So the underlying claim is that suppose that y and z inside of some smooth scheme X are subvarieties of complementary dimension. So that means the sum of their codimensions is the dimension of X. Then the multiplicity of y dot z at P is 1 if the following three things are true. So if, first of all, y and z are smooth at P. Second of all, the tangent space of y intersect with the tangent space of z is 0. And well, that's actually it. That's all you need. So the lemma that you should check. So this claim I'm not going to prove because I haven't said what this dot means. But the lemma you should check is that this is satisfied for the graph of phi and for delta. So you take y to be the graph of phi and z to be delta if x is smooth. So that guarantees the first condition, and 1 is not an eigenvalue. Of the phi action on the tangent space at P for P any fixed point for P any fixed point of phi. Okay, I mean this I think should be plausible. Like suppose suppose you have a high multiplicity fixed point. I mean that means that you fixed part of the tangent space, which means that 1 shows up as a eigenvalue. And Jose asks, yeah, so the sign comes from the degree of cohomology, and that's right. So ultimately it comes from the graded commutativity of the cut product. Okay, great. So in our example, very shortly, phi will be Furbineous, and the Furbineous action on the tangent space is 0. So 1 is not an eigenvalue of the 0 map. All right. Are there any questions about this? So yeah, maybe let me make an example. So the hypotheses of the lemma are true for phi x to x, the absolute Furbineous map. So here, for let's suppose x is x over fp is a scheme, and then we take x fp bar. Well, let me just take x fp. X over fp, and then this is the absolute Furbineous map. All right, are there any questions? Okay, so ultimately, let me make a brief interlude on Furbineous maps, because I think we have to do it now. Okay, so we're about to start proving the Weil conjectures. So now is your time to ask questions about stuff that's before the Weil conjectures. All right, great. So let's suppose that, let's see, what's the right way to say this? Yeah, so suppose X is a variety defined over a finite field FQ. So there are a bunch of different types of Furbineous maps, and I just wanna discuss them briefly. So first of all, there's the absolute Furbineous map. So this is called FrobQ, which is just a map from X to X, and it's over spec FQ. Right. So what is this map? It just sends a function f on X to f to the q. So it's a natural endomorphism of the identity functor. So what it means is that it's a map which maps any FQ scheme to itself, and it commutes with any two morphisms between FQ schemes. So it's a universally commutative map. It's extremely special. So its fixed points are the FQ points of X, but this is not a map of varieties over an algebraic closed field. So we can't actually apply the Lefschetz fixed point formula to it, right? Sorry, was there a question about this map?
Is that maps to supposed to go in the other direction?
I'm sorry?
That maps to the F maps to F to the Q?
It goes from left to right. How could it go the other direction?
Are they not functions?
Yeah, I mean, it's f here is a function on this X, and it goes to a function on this X.
Okay, fine.
Yeah, but you can't send f. Oh, I see. You wanted me to write it this way. Sorry. Yeah, I can write it the other way if you want. So f goes to f to the q if you'd like. Is that what you were?
Yeah, it's psychology.
Okay, yeah, that's fine. Great. But to apply this Lefschetz fixed point formula, we need to be over an algebraically closed field. So let's do that. So let's take x fq bar. That maps to spec of fq bar. And now we're going to take the absolute Furbineous here, prob q. That's a map from spec fq bar to itself. And we'll pull back along it. So we'll pull back, we'll take, so here, with this map. Okay, so the key observation is that if X is defined over FQ bar, so it's like you take a system of polynomial equations over if X is defined over FQ, So if x is defined over fq, this pullback here is isomorphic to x. I mean, even this map is an isomorphism, but there's also an isomorphism over fq bar. So can anyone tell me what that is? So the claim is that this is canonically isomorphic to x fq bar. So can anyone tell me what that isomorphism is? So it's just given by kind of multiplication. So let's just think in the affine setting. So in the affine setting, so let's suppose we have, so let's suppose x is spec of fq. I mean, it's enough to, if we make a canonical isomorphism, it's enough to do it in the affine setting. So suppose f is spec fq x1 through xn modulo some ideal. So x fq bar is just what we get by tensoring this with fq. So we get spec fq bar x1 through xn modulo the sort of ideal obtained by extension of scalars. So then what's x prime? Is this, it's spec of fq bar tensored tensored with fq bar over this over here we're tensoring, oh sorry, we're just tensoring these rings together, but we're viewing fq bar here as a module over fq bar via the Furbineous map. So here this is via the Furbineous map, which is an isomorphism. I mean, so but it's sort of a different module structure. Okay, but nonetheless, there's still a multiple. So it's enough to kind of make an isomorphism between these two things. Okay, and there's one coming just from multiplication on fq bar. So that's that. These two things are the same. If you were over a different ground field, like in general, that wouldn't be true. And if the coefficients, if this, you have to check that things respect I. So if I is not Furbineous stable, it's also not true. I mean, so this is really something about varieties defined over fq. All right, so what's our Furbineous morphism going to be? So there's now, we can take x fq bar. This is an fq scheme, even if it's not a finite type. And so it maps both to f spec fq bar and to x fq bar. So this top map is just the absolute Furbineous map. So it sends every function to its qth power. All right, so now we've mapped into this thing, we've mapped into this thing. That means we map into the fiber product by the universal property. So here we get a map like this, and that map is called relative Furbineous. So it's usually called map. It's the Furbineous of fq bar over fq bar. So the Furbineous of x fq bar over fq bar. So why is it called that? It's because it's a map from x fq bar to itself over spec fq bar, whereas the absolute Furbineous is kind of over this Furbineous map on the base. So this is something we needed to write down in order to get a map from a scheme to itself over an algebraically closed field. So the claim now, is that the fixed points, so the fixed points of this f, let me actually put a q superscript here, fq x fq bar over fq bar, which from now on I'll just call fq, are the fq rational points of x. Okay. And this claim is, I mean, don't want to say it's trivial because we wrote down this very complicated diagram, but it's trivial. So let me say why that is. So under this identification here, this map is just the identity on topological spaces. So on underlying topological spaces, so this map is the identity on topological spaces. So so the sort of the geometry of this map, so what this map does on underlying topological spaces. So this map sort of tautologically, its fixed points are the rational points. So whatever it does on topological spaces is exactly the same as what this does on topological spaces. So it's enough to check this for absolute Furbineous, and then for absolute Furbineous, it's obvious. Okay. So that's claim 1 about this map. And then claim 2 is that all fixed points have multiplicity 1. Okay, and let me just say a word about the proof of 2. So by our claim from before, it's enough to show that Furbineous, that FQ induces the 0 map on tangent spaces, because the 0 map doesn't have 1 as an eigenvalue. So can anyone tell me why that is? So why does Furbineous induce the 0 map on tangent spaces?
Because its derivative is 0.
Sorry, Ben, were you saying something? I'm having trouble hearing you.
Well, like the formal derivative is 0 because
Yeah, that's
Q
right.
is 0.
Yeah, so there's a couple ways to say this. So what Ben said is absolutely correct. That works. So here's the way I like to think about it. So suppose I have a map from spec, well, FQ adjoin T mod T squared to X, and then I compose with Furbineous. So this is what Furbineous does on tangent spaces, right? So you're taking Pth power. P is at least 2, so it kills T. That's the way I like to think about it. Okay. So that's the proof. All right. So we're now. So what do we know now? So let's begin to prove with the Weil conjectures. So proof of the Weil conjectures. So maybe let's maybe before we start proving the Weil conjectures, let's take a 1-minute break. Does that sound good? Since we've been going for 40 minutes now, I guess. No, 50 minutes. Well, this class is long. Yeah, so any questions on what we've done so far? So what have we done? We're trying to count rational points on varieties over finite fields. I'll remind you of the statement we're trying to prove in a second. But what we've done is we've just found a endomorphism of a variety over a finite field, or really its base changed at FQ bar, whose fixed points are our rational points, and now we're going to count fixed points. Okay, so I guess if there are no questions and no one says I want a longer break, I'll get started. So let's start with what we're trying to prove. So we're trying to prove rationality. So here, X is going to be a variety over a finite field. And what we want to prove is we want to prove that the zeta function of X, which let me remind you the definition. So it was exp of the sum from I equals 1 to infinity of the number of rational points over X FQ to the I over I times T to the I. We want to show that this is a rational function of T. Great. So strictly speaking, I only gave you the proof of Lefschetz fixed point formula for smooth projective varieties. So that's all we're going to prove for now. Later on, we'll talk about a slightly fancier version of Lefschetz, and that will if you just plug exactly this proof into that slightly fancier version, we'll get it for arbitrary varieties. But like right now, we'll just prove it for smooth projective varieties. So let's start the proof for X smooth and projective. So it's maybe a brief remark is it's not too hard to reduce to the arbitrary case to the smooth case, or you could reduce the arbitrary case to the projective case. That would not be very hard either. I don't know a simple reduction to the smooth projective case because we don't know resolution of singularities in characteristic P. Let me briefly think about it. Yeah, I don't see a simple reduction to the smooth projective case. So I think one genuinely does need a little bit more than what we've proven so far to prove the general case. All right, so let's write down what we know. So let me make a definition. So I'm just going to write trace of F on H star or FQ, X FQ bar QL. Maybe I'll just write it this way. I'll just write on H star X. So what I mean by this is the thing that we get from the Lefschetz fixed point formula. So it's the sum from I 0 to 2 dim X of -1 to the I of the trace of FQ star on, maybe move this to the left, acting on HI X FQ bar with QL coefficients. Okay, so what we know is that we know that the number of rational points of X FQ to the I is the trace of what I would call FQ to the I acting on H star X. So this definition I just made. So this is what the Lefschetz fixed point formula tells us. Okay, and then the observation one needs to check is that FQ to the I is FQ to the I, which is again tautological from what we wrote down before, but you have to check it. So this is FQ to the I. Right? So we can rewrite the zeta function now. So the zeta function of X is the exp of the sum. Let me rewrite it in terms of, sorry, this should be a 1, and it's 1 to infinity of trace of FQ to the I on H star X over, sorry, this should be an N, FQ to the N over N times T to the N. All right, can anyone help me rewrite this? So how are we going to show that this is a rational function? Any thoughts?
Just remove the sum. So pull the sum out.
Mm-hmm.
So they get a product then, because an exponential.
Yeah, so you could do that, but it would be an infinite product still, right? So I think it might be worth rewriting this a little bit first. So maybe yeah. So maybe there's another sum that might be worth pulling out. So first of all, it's enough to show that we can just, instead of having this alternating sum here, it's enough to show that the exponential of the sum from n equals 1 to infinity of the trace of FQ to the N just on HR of X. Okay. So it's enough to show. So here's t to the n over n. It's enough to show this with the star replaced with one of these cohomology groups. So can anyone tell me why that is? So ETS means enough to show. That is rational. So why is that? Yeah, so it's a finite product of rational functions. So it's because the zeta function of x is the alternating product of these as r ranges from 0 to 2 dim x. That's what the Lefschetz fixed point formula tells us. It just tells that it tells us that this trace is the alternating sum of these. So if you maybe this is what Jose meant. If you pull that sum out, you get just an alternating product of exponentials. Great. Okay, so can anyone help me rewrite this thing?
That infinite sum is like the determinant or the log of the determinant of.
Yeah, so how would you prove that?
Well, if it's diagonalizable, then it's pretty clear.
Yeah,
you
so
have to. Well, maybe you can argue that because it's generically going to be diagonalizable, then you can reduce to that case.
Yeah, I mean, so what you can do is it's enough to show it's a rational function over a bigger field, right? Like you can just go up to, you can replace those QLs with QL bars. And then you don't need that it's diagonalizable, you just need that it's upper triangularizable, right? So maybe without loss of generality, just by tensoring all these vector spaces with a bigger field, we can write trace of fq to the n on hr x fq bar ql as some sum of some eigenvalues lambda I to the n. So there's a bit of real content here. So we just use something really serious. So can anyone tell me what it is? And we've been using it throughout, like when we talk about traces of things. So here, this is a sum from I equals 1 to the dimension of HR. And we're using here, so the actual content here is that this is a finite dimensional vector space. So this followed from the finiteness theorems that I sketched earlier, which we proved via an induction on the dimension. So in this case, for example, it just follows from proper base change, from the finiteness part of proper base change. But it's a highly non-trivial theorem. So this is like in my opinion, so this as well as the input to the Lefschetz fixed point formula, so like the theory of Kunith and so on, is like the non-formal input to rationality. It's the finite dimensionality of these cohomology groups. Okay, so now we can write this as so this means let me call this function zeta x r. So it's the kind of piece of zeta coming from the Rth cohomology group. So this tells us zeta xr is exp of the sum from n equals 1 to infinity of the sum from I equals 1 to dimension of HR of lambda I to the n t to the n over n. Okay, now what is this? So this is the exp of the sum from I equals 1 to the dimension of HR of what? Anyone? So can anyone, what is this the Taylor series for?
For log of 1 minus lambda.
I think maybe it's negative log of 1 minus lambda.
Yeah, it is negative.
Yeah. So maybe 1 minus lambda I t to the t, I think is what it actually is. Right? So this is the product of 1 over 1 minus lambda I t, right? So I pulled out the -1 to make it 1 over, and then x of log is just the thing on the inside. Do you guys agree with this? Okay, and this is a rational function. Cool. Cool. Okay, so actually we can say a little bit more about it, right? So now what we know, in fact, is that zeta. Well, let me even write it this way. So if we take d, okay, so we just proved the first Weil conjecture. So there's a little bit more. So I claim, in fact, it's a rational function with integer coefficients.
Sorry, I guess the lambda I should be the QL coefficients.
I'm sorry? Yeah, so this
So
is shown right now that it's a rational function over QL bar, or QL, if you'd like.
All right.
Yeah, that's right. So we've now shown a priori we now know that it's in QLT.
Right.
Yeah, so strictly speaking, we had to make a base change to get these lambda i's, but if you stare at this, you'll see it's symmetric in the lambda i's. So in fact, what is this? It's like the reciprocal polynomial of the characteristic polynomial of FQ, right? So in particular, the coefficients of this actually lie in QL. So, but I claim, in fact, they're rational numbers, or at least we know that when we multiply them together. A priori, we don't quite know this yet, but we'll know soon that when we multiply them all together, so this zeta function, so this zeta x, we'll see very soon, will be actually a function with integer. We can write it as a rational function with integer coefficients. So can anyone tell me why this is? Well, let's just first take d log of it. Maybe that's the simplest thing to do. So d log of zeta x of t, if you just write out what it is, it's the sum of x fq to the n, I guess t to the n minus 1, I think we get. So this has integer coefficients. So a priori, there could be, we don't know yet, the zeta xr's have integer coefficients, although they do in the end. But a priori, that's because there a priori could be some cancellation happening between different r's, which doesn't show up here. But here, okay, you have to think a little bit about the exponential, which I'll let you think about. I mean, this tells you that you're fine up to a constant term, and then you can look at the constant term just by thinking like what happens when you plug in 0 here. Well, you get x of 0, which is 1. But yeah, so this tells you that in fact you ultimately get integer coefficients. Are there any questions about that? Okay, so Poincare duality, I'm not going to do in detail. Sorry, I shouldn't say Poincare duality. So the functional equation, I'm not going to do in detail. It's the same kind of analysis. So it's just you plug in Poincare duality. So let me just briefly say the point. The point is that hi of xql is dual to h2 dim x minus I of xql of d. So what that tells you is that this relationship between what I called zeta xr, so that was the zeta function of this, and zeta x 2 dim x minus I. So here with a t and here with like a q to the dt, and you have to work out what exactly this relationship is and then plug it in, and you'll see you immediately get the functional equation. Okay, so now we can start talking about the Riemann hypothesis. So this is what we're going to talk about for the rest of the course. So let me just tell you what the theorem is. So the theorem is we now have this rational function zeta xr. So the claim, first of all, is that this is a rational function. So maybe let me write it this way. So let me, instead of writing this, so let's look at the determinant of fq star t minus the identity acting on hr xql. So the claim is, first of all, the eigenvalues, sorry, the roots of this polynomial, so the eigenvalues, so the roots of this polynomial, sorry, let me just get rid of this. So here we have, let me just write a rigorous statement. So the theorem that we want to prove is that the Furbineous action on HR x fq bar QL has eigenvalues which are rational, which are algebraic numbers. And for any embedding of Q adjoin the eigenvalues, inside C, their absolute values are all equal. With the lambda I are all equal to Q to the R over 2. Okay, so and here X is smooth and projective. Okay, so we don't quite yet know that they're algebraic numbers. Leaving that aside for now, let me give you a couple examples where we do know they're algebraic numbers. So the main example is for hypersurfaces. And I'll discuss this a little bit more next time. So example, so we already know these eigenvalues are algebraic numbers in a lot of cases. E.g. for hypersurfaces. So can anyone explain to me why this is the case? So we'll need there's a vanishing theorem that we need to use that I only mentioned briefly, and I didn't say anything about the proof, and we'll need to use it a bunch. So I'm actually going to prove it next time probably. So but let me just make here hypersurfaces means smooth projective hypersurfaces. So suppose we have X inside of Pn, which is a smooth projective hypersurface. So what does its cohomology look like? So the cohomology of X, QL, first of all, for star less than the dimension of X, it's just equal to the cohomology of Pn with coefficients in QL. So this is called the Lefschetz hyperplane theorem. So I haven't proved this yet. It follows from a statement I mentioned earlier, which is that the cohomology of affine varieties vanishes in degree at least the dimension. So in particular, the complement. So maybe I'll just erase this bracket. So this is because Pn minus x is affine. So and then plus the excision sequence. So what we need to prove this is that the cohomology of affine varieties vanishes in high degree. So what you really get at here is that the cohomology in degree when you apply excision. So really you need excision and Poincare duality here. So what you really get when you, and I'll sketch this next time, but what you really get when you apply excision here is that the cohomology of x is the same as the cohomology of Pn with a twist in high degree. And then Poincare duality gives it to you in low degree without the twist. So what this implies, if you apply Poincare duality, is that we know h star of x QL is a twist of QL unless star is equal to the dimension of x. So what this tells us is there kind of can't be any cancellation. So we know that all the roots and poles of the zeta function of x are algebraic numbers because we know the zeta function, the whole zeta function is an integral rational function. And then we know that the only thing that could contribute interesting eigenvalues is the middle cohomology. So that tells us that the middle cohomology has to have eigenvalues which are all rational functions. So at least in many situations, we already know this first part. So the actual content of the Riemann hypothesis is the second part. And I'll explain how to use similar results, similar arguments to do this first part in general. So this part, what I wanted to say before next time is just that this part is kind of easy given what we've done. And then this part is really hard. All right, so next time we're going to start on Deligne's proof of the Riemann hypothesis. So I'll explain this. I'll do a bunch of reductions, which will also involve a similar Lefschetz argument, and then we'll begin the real meat of the proof. So are there any questions about that?
Do we need other preliminaries to prove Deligne's method?
I'm sorry?
Like, do we need some preliminaries on Lefschetz pencils or?
So I'll do those during the proof. I think it's time we just get started. So yeah, there will be a lot of preliminaries that show up in the proof, but they'll be digressions rather than me just telling you more facts.
Okay, I see.
Well, I'm going to actually try to sketch the proof next time.
Right.
And then we'll fill in details. All right. Any other questions? All right, if not, I'm going to stop recording then, and I'll see you all soon.